Alrighty, so this video we will work out a few example problems for rotational kinematics, the last lecture we just had. Before I do, of course, let me write down the equations. If you remember, there are old basic kinematics equations, but with the new rotational variables. So theta is omega naught t plus 1/2 alpha t squared. Omega f squared is omega naught squared plus 2 alpha theta. And alpha is omega f minus omega naught over t. And we found, if it's helpful, that the linear variable is equal to the angular variable times the radius of the orbit. I keep doing that. Omega. X is theta times r, A is alpha times r. So these equations on the right, they allow you to convert between linear and angular variables. So if you're told a bicycle wheel is rotating at 4 radians per second, and I wanted to know how fast, what's the linear speed of the rim of that wheel, you would use these equations to calculate it. All you'd have to know, of course, is how big is the wheel, what's the radius of the wheel. Anyway, these were the equations, and so we want to, try working out a few examples and see how to use them. So let's start with the first example. And this is a pretty interesting question. The question is, what is the angular speed of the minute hand on a watch or a clock, the old analog clocks? So this is pretty interesting because seemingly you don't really have much information. There's no numbers given or anything like that. So we have to use a little intuition here. We have to think and use some logic. We want to know omega. We're looking for omega. That is the angular velocity, the angular speed of an object. What object are we looking at? The minute hand on a clock. Okay. What do we know about the minute hand? Well, what we know is that the minute hand does one complete revolution around the face in 1 hour, right? When a minute hand goes from 12 all the way back to 12 again, it's changed 1 whole hour. So what we want to know is 1 revolution per hour. Omega is 1 revolution per hour. But revolution per hour is bad units. What we want is radians per second. So this is basically a conversion. Can we convert revolutions per hour to radians per second? That's all we have to do. Well, let's see. First thing we do, we're going to multiply by something. What we want to do first is get rid of the revolutions. So revolutions being on top, and you put revolutions on bottom here. And what do I know? That for 1 revolution, there's 2 pi radians. If I do that, the revolutions cancel. And I'm left with radians on top, which is good. However, I still have the hours sitting there. Hours is bad. So I want to multiply by something. I want to multiply getting rid of the hours, and since hours is on bottom, I need to put the hours on top over here. And a conversion I know is that in 1 hour, there's 3,600 seconds. And that would cancel out the hours. Now, of course, if you don't know 3,600 seconds in an hour, you could do 1 hour is 60 minutes, and then 60 minutes, and then 1 minute is 60 seconds, and you'd get the same thing. But here, I just know 3,600 seconds in an hour, so there we go. If I multiply across, I'll get units of radians per second, which is exactly what I want. So let's do it. 1 times 2 pi times 1, that's 2 pi on top. And on bottom, I have 1 times 3,600. Well, let's simplify. 2 cancels this, makes this 1,800. So I get pi over 1,800 radians per second. And of course, if you had a calculator, you could plug it in and get some decimal, that's fine. But this is good enough. So that's an interesting question. It's kind of weird. We're used to questions that have a bunch of numbers in them, and we plug it into an equation, but this was more of a conceptual question. Can you think your way through? You're told you're looking at the minute hand of a watch, and you want to know how fast it moves, the angular velocity. And so you have to think, what do I know about the minute hand? The minute hand goes 1 whole revolution, and it takes an hour for that to happen. What if I were asking about the second hand? What's the angular velocity of the second hand on a watch? Well, I know the second hand goes 1 complete revolution in 1 minute. So then I'd be converting 1 revolution per minute to radians per second instead. Or the hour hand. The hour hand makes 1 complete revolution in 1 day, or 24 hours. And so I'd have to convert that either way. So that's the first one I wanted to do for you. Next example. A little more like what we would normally do for this type of stuff. Let's say we have 10 seconds after an electric fan is turned on. The fan rotates at 250 RPM. What must be its angular acceleration? All right. So this is more like a true kinematics problem. So I'm going to try to solve it like a kinematics problem. First thing I do is I write down what I know and what I'm looking for. 10 seconds after, so I know T, the time it takes to do something is 10 seconds. After an electric fan is turned on, the fan rotates at this velocity. So it gets up to some final velocity of 250 RPM. And I'm told the fan was turned on. So that means originally it was off. It wasn't moving. So that tells me the initial velocity was 0 radians per second. And I'm looking for alpha. All right. Well, before I even think about trying to solve this problem, there's an issue. The issue is the units of one of the things of data is bad units. RPM, that's bad units. So the first thing I need to do is convert to get the correct units. So 250 revolutions per minute. I need to convert to radians per second. So let's do our conversion. 1 revolution on bottom cancels him, and I know there's 2 pi radians. All right, next I need to get rid of minutes, so I know in 1 minute, second cancels out the minutes, there's 60 seconds. And so now if I multiply through, I get radians per second, which is exactly what I want. So I'm going to multiply 250 times 2 times pi, and then I divide by 60, and I get this final velocity to be 26.18 radians per second. Now, all I have to do is start thinking about which equations to use. I'm looking for alpha. I know final velocity, initial velocity, and time. So I'm going to use alpha is omega f minus omega naught over t. So plug my numbers in. Omega f, 26.18, minus omega naught, that was 0 because it was originally off. Divide by time, 10 seconds, and I get alpha must be 2.618 radians per second squared. So, not too big of a deal. Nice little question. Of course, we did have to convert because the units were wrong, but that's not hard. We know how to convert. As long as you're in radians and seconds and things like that, you're good. All right, let's try another example. Let's see, what else do we have? All right, a wheel has an angular velocity of 20 radians per second clockwise. If it has a constant angular acceleration of, let's say, 5 radians per second squared to slow down, how long will it take for the wheel to have an angular velocity of 10 radians per second counterclockwise? And then we could also ask part B, through how many radians does the wheel turn? Okay. So 2 questions. Number 1, you have a wheel. It's currently spinning clockwise. You then flip a switch on the motor or whatever, which creates an acceleration to slow that wheel down. So in other words, it's the acceleration's in the other direction. Eventually, the wheel slows down to a stop and then starts speeding up in the other direction, the counterclockwise direction. And you want to know, how long does it take to go from 20 clockwise to 10 counterclockwise? And then, once you know that, you want to know, how many times does it spin? What's the angular displacement? Through how many radians does the wheel turn? Okay. So, again, let's start with writing down what we know. The wheel has an initial angular velocity of 20 clockwise. Now, I'm going to have to choose which direction do I want clockwise, positive, and which negative. It's up to me. It doesn't matter which I choose as the positive direction. Let me go ahead and say counterclockwise is positive. In fact, let me write it in red. Counterclockwise is positive. Okay? So that means clockwise stuff will be negative. All right, so initial angular velocity, omega naught, is 20 clockwise, so it's negative 20. It has an angular acceleration, alpha, of 5, and that's to slow it down initially. When it says that, don't think of slowing down or speeding up. Think of the direction of the acceleration. So, first of all, before you think about it in terms of rotation, think about a car. A car is moving to the right, then it slows down and begins moving to the left. Okay? The direction of the acceleration of this car is leftwards. So, the initial velocity is to the right, the acceleration is to the left. That's what slows it down. Now, when you do that, you choose directions to be positive or negative. If the car is moving to the right, I'd say that's a positive velocity. The acceleration points to the left, that's a negative acceleration. The fact that it's slowing down does not make the acceleration negative. The direction of the acceleration is what makes it negative. Okay? So, let's say a car was moving to the left. It's driving along to the left, slows down, comes to a stop, and starts moving to the right again. Well, that is, initial velocity is to the left, with an acceleration that points to the right. Well, I would say a left initial velocity is a negative velocity, and acceleration must be positive, because it's to the right. Even though technically the acceleration is slowing it down, it's a positive acceleration. And the reason is, positive and negative goes with the direction, not with whether it speeds up or slows down. So keep that in mind. Here, this acceleration says it slows down the wheel. What that really tells me is, since the wheel initially was going clockwise, the acceleration must be counterclockwise. I've chosen counterclockwise stuff to be positive, so this acceleration is a positive acceleration. All right. Question, how long will it take, so t I'm looking for the wheel to have an angular velocity, so the final velocity, of 10 in a counterclockwise direction, so he's positive. And then lastly, part B, through how many radians does the wheel turn? That's what is theta? What's the angular displacement? All right, there we go. So now that I have all my information laid out, I can start using equations. I have initial velocity, I have final velocity, I have acceleration, I'm looking for time. That's alpha is omega f minus omega naught over t. I want to solve this for t, so I'll multiply the t over to the left and then divide the alpha back. So this becomes t is omega f minus omega naught over alpha. And now I plug my numbers in. Omega f, positive 10. Omega naught, negative 20. Over alpha, positive 5. So 10 minus negative 20, that's 30, divided by 5 becomes 6 seconds. So it takes 6 seconds for this to happen. And now let's look at part B. Through how many radians does the wheel turn? I'm looking for theta. So what do I want to use? Do I want to use, I've got two options. Theta is omega naught t plus 1/2 alpha t squared. Could I use it? I'm looking for theta. I know omega naught. I just calculated t, and I know alpha. I can use this, but in order to use it, I have to use t, which I calculated, and that might be wrong. Well, that's okay. Let me go ahead and do it anyway. What do I get? Negative 20 times t plus 1/2 times alpha times t squared. So negative 120, 36 divided by 2 is 16. 16 times 5 is 80. And so I get negative 40. I'm sorry, this is 90. Not 80, 90. Negative 120 plus 90 is negative 30 radians. Or 30 radians in the clockwise direction. Either way, you could say negative 30. But let's say I did not want to use this equation because I was unsure of my t. What's the other equation? Omega f squared is omega naught squared plus 2 alpha theta. I want to solve this for theta, so I get omega f squared minus omega naught squared equals 2 alpha theta. Divide by 2 alpha, and that will give me theta. So theta is omega f squared, which is 10 squared, minus omega naught squared, which is negative 20 squared, over 2 times alpha, which is 10. I'm going to plug this into my calculator, so I get 100 minus 400 over 10, and I get negative 30. So, of course, I get the same answer. And that's because my time, I solved correctly. But you can see either of the equations would have given me theta. It just depends on which one I wanted to use. But again, here we have an example, a nice kinematics problem. Write down the information in the problem, look at the equations you have to work with, and just choose which equation you can use. Be careful about your positives and negatives, your directions, because of course that matters. And at the end of the day, you're plugging numbers into your equation and solving them. We're not doing X and Y component stuff. We're not doing anything like that. No sines and cosines. It's purely take the information in the problem and use the correct equation. So I hope these few examples kind of give you a good idea about how to use the equations, how to go about thinking about these problems. There's a good amount of practice problems posted on Canvas right now, as well as the solutions. Work through them, make sure you're understanding. Some of the solutions I have, pi in it, like negative pi over 20 or things like this. If you want to give me the decimal, if you don't want to keep pi, that's fine. I don't mind when I'm grading tests. If it's a decimal answer, that's perfectly fine. It's just, for me, when I calculate stuff, I don't tend to use calculators. And so I have a lot of fractions, and I like to keep pi as pi, just because it's too difficult to try to, stick pi in there as a decimal answer. But you're certainly welcome to use a calculator, plug pi in and all of that stuff. I don't need fractions, decimals, it's fine. But anyway, work through these problems, make sure you understand them, and be on the lookout for the next topic, which is going to be on the rotational version of force, which is called torque. So, until then.